what we're going to do is we're going to look at the periodic table and some of the predictive powers of it, as well as some information about its organization. The periodic table that we have now was predicted or put together in the 1960s by Mendeleev. And what he did was he took all of the known elements and arranged them by their mass, and then he started breaking them up into a table with columns and rows. And based on what they knew at the time, he broke the tables up every 8 elements. And what he found was that upon doing this, elements that ended up in the same column shared chemical and physical properties. And elements in the same rows also shared some properties. And so therefore he called the columns or groups, because of their shared chemical and physical properties, groups or families. Okay? And it's called a periodic table because the patterns repeat. And the beautiful nature of his table is it allowed him to predict the presence of elements that were not known. Now, our modern periodic table, rather than using our atomic mass, we use our atomic number, or the number of protons in the nucleus. Okay? And remember, we talked before when we were looking at our Bohr-Rutherford diagrams that when we look at each element's square in the periodic table, we have a number of different things. We have our element symbol, we have our element name, we have our atomic number, and we have our atomic mass. Remember, which is our number of protons plus our number of neutrons. Okay? Now, if we take our periodic table with our 118 known elements, we can take these elements and we can break them up into different categories. The simplest set of categories that we can break them up into is what we call metals, nonmetals, and metalloids. And their classification in each of these is due to a series of properties. Now, we've looked at these physical properties already and talked about them. The fact their state at room temperature, their ductility, meaning whether or not they can be drawn into a wire, their luster, are they shiny or dull, are they malleable, can we hammer them into shapes, conductivity, do they conduct electricity and heat? Okay? So, the largest category of elements in the periodic table are our metals, and they take up a wide swath of them. And we could take our metals and break them up into other smaller groups, but the vast majority of the elements on the periodic table do fall in the category of metals. And we know that metals are solid at room temperature, they are shiny, so they have luster, they can be hammered into shape, so they're malleable, they can be drawn into a wire, and they're very good at conducting both heat and electricity. This is why we use them for wires and why we use them to make our pots and pans. And we have a wide variety of them, for example, copper, nickel, zinc. Okay. Our second smallest category is our nonmetals. Okay, and they include most of the elements on the right side of the periodic table, but also hydrogen, even though it's over on the left. Okay? And the properties of our nonmetals are pretty much the opposite of our metals in many cases. Our nonmetals, unlike the metals, can come in multiple states at room temperature. Metals can only be solid, but our nonmetals can be solid, liquid, or gas. They're dull. They can't be hammered into shapes. They can't be drawn into wires. And they're poor conductors of both heat and electricity. Now we have a very small group of elements which form sort of a transition zone or boundary between our metals and our nonmetals. And we call them our metalloids. And they share properties of both our metals and our nonmetals. So our metalloids have properties of both our metals and our nonmetals. Most of them are shiny at solid at room temperature. They tend to be shiny, but they're brittle, and they can be drawn into wires. And they're moderate conductors of both heat and electricity. So they have unique properties. For example, silicon. Now, Mendeleev said that elements in the same column would belong to a group or family because they shared similar chemical and physical properties. So we have a number of groups or families in the periodic table that are of particular interest to us. And our first one is our group 1, or our first column, and we call them our alkali metals. And they get their name because of how they react with water. Okay, and they include metals like lithium, sodium, potassium. They're highly reactive with water and other elements, and we'll only find them in compounds. And they're compounds that are soluble in water, called salt, and they have one valence electron. They're often called true metals, so they show lots of the properties of other metals. But one difference between these metals and others is these metals actually are very soft, and we can cut them with a knife. Our second group that we're interested in are called our alkaline earth metals. These are group 2 metals. Okay? These metals get their name because they are usually found combined with oxygen in the Earth's crust. For example, calcium oxide makes up a good portion of the Earth's crust. Okay? And the metals in this group are beryllium, magnesium, calcium. They are still very reactive with water, but less reactive than group 1. They form insoluble compounds in water, and this is why they make up a good portion of the Earth's crust. But one of the nice things about these chemicals is they burn in bright colors, and this is why they get used in things like fireworks. And for another point of interest that we'll talk about, they have 2 electrons in their outer orbit. We have our transition metals. Okay, these have a variety of properties. Okay, they include iron and copper. They conduct heat, electricity. They have many uses. But one of the cool things about transition metals is they can form solutions of multiple colors. Okay, metal solutions of group 1 and group 2 metals tend to be colorless, but solutions with metals in the transition metal range are very colorful. Our next group or family that we're interested in is what we call group 17 or 7, and these are our halogens. Okay, and our group numbers go from group 1 here on the left, 2, 3, 4, 5, 6, 7, all the way up to 17. Okay, sometimes you'll see them count numbered 1, 2, we're going to skip all the short, 3, 4, 5, 6, 7. And I'll tend to refer to them as group 1, group 2, group 3, group 4, group 5, group 7, group 6, group 7, group 8. Okay, I'm going to go with the lower numbers. I'm going to ignore the transition metals when I number, and I have a reason for that, as we'll learn in next week. Now, our halogens, they're all nonmetals. They're colorful, so they have different colors. They tend to be gases if we're near the top of the group, but their state changes as we go down the group. Okay, they're only found as compounds in nature, and they have 7 electrons in their outermost orbit. They're very reactive. Our last group, in group 18 or 8, are called our noble gases. Okay, they're nonmetals, they're very stable, they don't react. That's why they're called noble gases. But when we pass electricity through them, they glow in different colors. So if you've ever heard of a neon light or a xenon light, that's where these elements are found. Okay, and they have 8 electrons in their outermost orbit, or it's full.